In aviation field, there is a normal operation called go-arounds. Go-around is initiated by pilots or controller to avoid landing of an aircraft under unsafe conditions, such as vehicle on the runway. The goal for this project is to model the relationship between factors of interest and go-arounds. The second task is for prediction. Given the whole trajectory on the left, I detect go-arounds before and the results will be used as ground truths. For the prediction, I only know part of the trajectories and predict whether these flights will have a go-around in the future. The final dataset has 489 go-arounds over 140,000 flights. Due to multicollinearity, I apply PCA to the mixture of categorical and numerical variables and regress on the principal components instead of the original features. Insignificant principal components are removed. One way to interpret the result is to calculate the matrix product of a model estimate and our loading matrix. Then we can get a coefficient estimate for each original variable. All variables interpretation consist with y expected. For example, increase the airport visibility will decrease the go-around probability. The second word is for prediction. Considering that the cost of missing a go-around is more expensive than a controller or pilot receives a false alarm. So I want a high recall score and also relatively high precision score. The first model I tried to plug in the estimates from the previous model. Since model is selected based on the significance level, so no need for cross-validation. The upper row is the ROC curve and precision recall curve for training set. The bottom row is for test set. From the confusion matrix, only half of the go-arounds are detected. The second model is to apply PCA only for continuous variable and use ad hoc method for categorical variables. Model selection based on cross-validation, and all the models will resample to balance the class weight, but the performance barely changed. The third model is not using any PCA. With the original features, the recall increased roughly about 10%. So from now on, I will only use the original features for prediction. For the bagging, although it's overfit, I got similar recall score and much higher precision score. The random forest can predict 90% of the go-arounds, but also gets wrong warnings 90% of the time. The AdaBoost model can predict 70% of go-arounds. But when we apply the undersampling technique, the model is overfit. I visualize two features altitude and speed here. Many go-around samples are actually overlapped with the normal flights, at least in this two feature space. In summary, the AdaBoost has the best performance in terms of the recall score. The imbalanced class problem is hard because its decision boundary for separating out the extreme event must be very nonlinear, but I think this is a good start for this study. Thank you.